whole new space race has begun. Over the next decade, the United States, Japan, India, China, Russia, and even private companies are planning to send spacecraft to explore the moon. They will map the lunar surface, monitor the soil for moonquakes, study the flow of heat from the moon's core, and prospect for water deep within. What they are looking for goes beyond science. These missions are looking for resources that may one day allow humans to settle permanently in space. The moon race is now heating up in the wake of discoveries made by a mission known as L-Cross. What did scientists see in the debris of a rocket they sent crashing into the moon?
Six, 5, 4, 3, 2, 1. Ignition and liftoff of Ares 1X, testing concepts for the future of new rocket design.
There was a time when only government agencies had the ability to blast rockets into space or send missions to worlds beyond our own. These days, countries around the world are preparing to send missions to the moon. They are joined by a rash of private ventures. Their interest goes beyond exploration. They see a chance to make money by supplying launch or human transport services, including tourism. Some hope to begin exploiting space resources like energy or rare minerals. Over 30 private robotics teams are now vying for the $30 million Google Lunar X Prize, a contest designed to spur the building and launching of rovers equipped to explore the lunar surface. It was inspired by the Orteig Prize that sent Charles Lindbergh flying across the Atlantic Ocean more than 80 years ago. That feat helped launch the civil aviation industry. The sponsors of this prize hope it will unleash the entrepreneurial spirit into space. To many, lunar exploration is the first step in fulfilling one of the great promises of the space age: to send humans to the moon and beyond, to permanently live and work in space. Preparations for that day are taking place right now aboard the International Space Station, where astronauts are developing a whole new way of living. To stay healthy, for example, they are working out routines for exercise and nutrition to keep muscles and bones from weakening and thinning in zero gravity. Just as important, they are developing technologies that ensure clean air and water, shelter from solar radiation, and flexible spacesuits to work and explore in hostile environments like the Moon. Our fascination with the Moon, Earth's traveling companion, goes back to the dawn of humankind. As the brightest object in the night sky, the Moon has guided people for millennia by defining the rhythms of life and animating our myths. Its true nature began to come into focus 4 centuries ago. Galileo Galilei had heard of an instrument built by Dutch opticians that was capable of seeing faraway things as though nearby. In many ways, the first modern scientist, Galileo saw this new instrument as a tool to help settle a long-standing question. What was the nature of the heavens, and how did the world of men fit within it? To some philosophers, the Moon was a perfect crystalline sphere of divine substance, free of Earth's imperfections. Galileo, with his telescope, saw a more familiar reality. He noted mountains and valleys on the Moon, features like those of Earth. Flash forward to the modern age of lunar studies. 1959 saw the first in a fleet of probes launched by the Soviet Union and the United States to shoot close-up pictures, take direct readings, and crash onto its surface. We learned then just how different the Moon is from Earth, with its barren landscapes and its network of craters. Finally, the astronauts of Apollo piloted down to the lunar surface to get a close-up look. The Moon, these astronauts discovered, is like a time capsule from the early days of the solar system. Evidence from rocks they gathered helped support a dramatic theory that the Moon is actually made of material very similar to the surface of the Earth. It likely formed more than 4 billion years ago, when Earth, in its infancy, collided with a planet that was about the size of Mars. When the dust settled, the debris began to coalesce in Earth orbit, forming the Moon. By then, volatile compounds like water had evaporated. From this violent beginning, the Moon gradually cooled, and the magma that lined its surface hardened into a crust. Yet it was still subject to intense bombardment in the chaotic environment of the early solar system. Its surface has been hammered by large impacts at every stage in its history. Scientists began to wonder whether those impacts had endowed the moon with resources, such as water, that could be tapped to support long-term manned missions. The 6 Apollo crews had touched down near the equator. Buzz Aldrin, the second astronaut to step onto the lunar surface, described what he saw as beautiful, beautiful, magnificent desolation. He and the others found that the lunar surface is utterly dry, with no signs that water had ever flowed there. The main reason is that there's no atmosphere. Any water would have long since evaporated into space. But there's more here than meets the eye. It turns out that the rocks these astronauts brought back to Earth were loaded with hidden treasure: iron oxide, calcium oxide, and other compounds that contain oxygen. To confirm this finding, astronomers trained the powerful eyes of the Hubble Space Telescope on the lunar landscape. What could a telescope, able to see galaxies 10 billion light-years away, tell us about an object we can practically reach out and touch? From its position in orbit, Hubble's instruments are able to read the ultraviolet light that is blocked by Earth's atmosphere. Using Hubble's spectrograph to dissect the light being reflected off the lunar surface, astronomers searched for the fingerprints of specific minerals. Their first lunar targets were the landing sites of 2 Apollo missions. Analyzing rock samples from these sites, they had found a glassy material called ilmenite, a mineral that's rich in oxygen. Hubble's data showed that ilmenite is strewn all over these sites. Hubble moved on to a second target, the Aristarchus crater, 25 miles wide and about 2 miles deep. Created by an impact 450 million years ago, a recent event in cosmic history, it's one of the youngest large features on the moon. The impact had exposed the ground below, and with it, the history of a region rocked long ago by impacts, volcanic explosions, and shifts in the moon's crust. This region, too, is rich in ilmenite, and therefore oxygen. But what about the other element that makes up water? Hydrogen. In 1998, from lunar orbit, the Lunar Prospector mission recorded the telltale signatures of a variety of elements. One of them caught the eye of scientists. The data showed that hydrogen is spread widely across the poles of the moon. If it's a tracer for water, then millions of tons of ice could well be embedded in the soil. Scientists began to suspect that water ice may actually be concentrated in large enough quantities to support a human settlement. It would not be on the open plains or on the sides of mountains. The best places to look are at the poles, on the floors and sides of deep craters, where the sun never shines. A good example is the famed Shackleton crater at the South Pole. It's named for the fabled explorer of our own South Pole, Ernest Shackleton. If there is ice in places like this, It might have been delivered by the asteroid or comet that hollowed out the crater in the first place. It might also be from vapor kicked up by more distant impacts. Some may say that past missions have only scratched the surface of the moon. A recent mission known as L-Cross was designed to change that in a spectacular way. As it approached the moon, the L-Cross upper stage separated, beginning a free fall. Its target, the 97-kilometer-wide Cabeus crater at the South Pole. The lower stage trailed above and behind, equipped with a battery of infrared and visible wavelength cameras. Seconds after it slammed into the crater, the trailing lower stage detected a tenuous cloud rising up. In the cloud was a mix of carbon monoxide, ammonia, methane, and more. It turns out that 5.6% of the crater floor is composed of water ice, a higher concentration than some areas on Earth. This water might have been delivered by comets striking the moon over the eons. There's another explanation, one that recently emerged from the study of rocks gathered by the Apollo astronauts. The samples are graced with tiny glassy globules, minerals melted in the crucible of lunar volcanism. Analyzing these Apollo rocks with new techniques, several teams of scientists have found a compound called hydroxyl. It's H2O with only one H. It's an indication that water may be much more abundant than anyone thought. We don't see it because it's locked up inside the moon. Scientists think there might be enough there to cover the lunar surface with a layer of water 1 meter deep. The presence of water is good news for explorers who dream of one day spending quality time on the moon. It will allow them to go after the real prize they are seeking. Back in July 1969, astronaut Neil Armstrong departed slightly from the mission plan and scooped up some dirt. He used it to fill out an empty space in a sample container and brought it back to Earth. The dirt had been lying on the moon for millions, if not billions of years, soaking up the sun. Scientists found that solar winds had endowed that dirt with a substance rare on Earth called helium-3. It's a potential fuel source for interplanetary travel or for large-scale power generation on Earth, and there appears to be a lot of it there. An even bigger draw is likely to be abundant stores of lunar platinum, deposited there by comets and asteroids. According to one would-be prospector, a platinum mining operation on the moon would cost about $20 billion to set up, but it would earn twice that amount every year. If and when people do return to the moon, the poles may offer the best chance of finding water. But try landing there. The light is dim, and sharp shadows turn the ground ink black. Engineers at NASA's Jet Propulsion Lab have been working on special sensors to read the landscape and safely guide lunar vehicles to their landing sites. One of them is called LiDAR. It's a laser that emits pulses of light 8 times per second to produce a 3D picture of the surface below. On the way down, automated navigation systems can be programmed to avoid rocks and the slopes of craters to find the smoothest places to set down. Meanwhile, NASA's Lunar Reconnaissance Orbiter, or LRO, has been scoping out safe landing spots in the most ambitious lunar mapping project to date. Like a lunar spy satellite, the LRO has been scanning the surface of the Moon with a multitude of instruments. It uses a laser, for example, to survey the topography. When the light bounces off the surface and returns to the orbiter, its timing and intensity reveal the location of steep slopes and rough terrain. Another instrument records the temperature. Where there is lots of loose material, temperatures change more slowly from day to night. So a thermal map can show places where the ground is too rocky or too soft for a landing. Finally, the orbiter trains a high-resolution camera on the surface. This will allow mission planners to actually pick out large boulders. In this simulation, the red areas are clearly unsafe, while the green are smooth and free of hazards. Few places on Earth have been scanned so thoroughly. And within the data, planners hope to uncover places that are not only safe, but worth exploring. "40 years ago, the Apollo astronauts showed that we could overcome Earth's gravity and set foot upon the Moon. But they did not stay for long. Today, we are making plans to go again, emboldened by evidence that we can find the natural resources to extend our stay. As unlikely as it seems that people would live permanently amid the magnificent desolation of the Moon, there have always been those among us willing to strike out for points unknown, to challenge our limits. Whether it's for adventure, profit, or the pursuit of knowledge, it seems likely that one day we will extend our reach out beyond Earth, into the solar system, and even beyond.